Okay, so today I'm going to lead this paper and by Xiaotao Yang and Haiying Gao. And title is Segmentation of Aleutian Alaska Subduction Zone Reviewed by Full-Waveform Ambient Noise Tomography. Implication for long strike variation of mechanism. Since I think most of you are non-seismologists, except for some of my students. So you're welcome to interrupt me and stop me anytime if you have any questions about, anything about seismology. Okay. So just a few words about the author and the speaker this Wednesday, Dr. Xiaotao Yang. And this is an interesting figure I found here from his website. I think it summarized very nicely of his research area, which essentially, like every seismologist, just use seismic waves to understand the internal structure of Earth under various technical settings, such as subduction zone, mountain, later pointer, mountains and basins and rifts. I think in the three papers and Zhang Dou sent to us, it covers the topic of subduction zone and probably basin and rifts, and maybe cover a little bit about mountains of eastern US. So he's also interesting to understand the earthquakes as well as to study the kind of earth seismic hazards. And Xiaotao, he got his bachelor and master degree from China. And then he went to US and got his PhD in Indiana University. After that, I think he had 2 terms of postdoc appointments. And the first one is at University of Massachusetts Amherst. And then he went to Harvard for another year and 2 months. And after that, he joined Purdue University as an assistant professor in August 2020. So that's about Xiaotao. And then about today's topic, today's paper. So this is a very traditional and typical seismological paper, essentially just use seismic waves and to image the upper mantle and lithosphere structures of certain area. And in this case is the Alaska Aleutian Subduction Zone. So this is figure 1 from their paper. And the left one shows the tectonic settings of Alaska Aleutian Subduction Zone. And as you can see that the Pacific plate is moving towards the north and subduct beneath the North American plate at the Aleutian Trench. And the dashed box actually encloses the image area. And we can see that those kind of right triangles, they are the volcanoes. We can see there are like 3 distinctive volcano clusters. And the first one is called Aleutian Arc, AA here. And then in the northeast, we can see there are like two volcanoes. It is called BCJD. Name is quite long here, so I just use BCJD for short. And the third group is the WVF group over there. So there are like 3 independent and separate volcano groups in this area. Aside from these 3 groups of volcanoes, as you can see, there is like a gap area, right? We don't have the volcanoes. So this is called Denali volcanic gap. And the point of this paper is trying to understand why we have such a kind of distribution of volcanoes as 3 clusters, as well as why there is a gap, very interesting gap in between these 2 volcano groups. So the right figure shows here is the station distribution, and those blue rectangles are the seismic stations used in the study. Most of them are coming from US array, with some additional instruments from Canadian National Seismograph Network deployed here. So, okay, since this paper have been talking a lot about subduction, volcanic arc, and full arc and back arcs. So I just want to make sure everybody is on the same page. So I can kind of briefly introduce the structure of the subduction zone. So this is a kind of a very, I think it's kind of a famous paper and by Roy Hyman and Claire Curry. And it just summarizes very nicely the structure of the subduction zone. So if you cut across the subduction zone, like if you cut across a line here, and the cross section is gonna look something similar to this. So on the left, we have the subducting oceanic plate. In this case, is a Pacific plate. And then on top of it, we have the volcanic arc. So the region in front of the volcanic arc is called forearc. Okay, and on the other side of the volcanic arc is a back arc. And it has quite interesting geophysical characteristics, such as it has high heat flow. And then in the upper mantle, it has a low seismic velocity because of the warm thermal regime. Okay, so don't worry about this. This is a craton, so it's irrelevant to the Aleutian Alaska subduction zone. Okay, so I think I summarized like two main science questions investigated in this paper. And the first one, well, you mentioned in the paper is how and where magma is produced, transported, and accumulated, and why volcanoes are clustered. So I think in short, it's basically trying to investigate why there are volcanoes. Okay, and another one is basically the cause of that Denali volcanic gap, and because there have been series, a contradicting series, trying to explain why there is a volcano gap. So in short, it's basically trying to answer this question: why there are no volcanoes? So why there are volcanoes and no volcanoes? That's two questions, scientific question investigate in this paper. So I think because in this paper it doesn't talk much about methodology, but I think it's kind of one of the punchline in this paper because it uses this kind of advanced seismic imaging method. So I think I'm gonna briefly just explain to you guys, non-seismologists, and also some of my students, and they are not working on seismic imaging. So I'll just briefly explain what is ambient noise, full-waveform inversion. So don't worry too much about ambient noise. You can just treat it as earthquakes, and don't worry too much about ambient noise. This is quite popular technique in seismic imaging. So about full-waveform inversion. Okay, so this is a figure from Haiying Gao. Her 2014 Nature Communication papers. So this basically explains what is waveform inversion. Essentially, here the black curve is observed seismogram, okay? And the red curve is the synthetic seismogram. So the idea is we're going to modify the synthetic seismogram is generated by running the simulation with some velocity model. So the idea is we modify the velocity model, modify the model parameter such that the observed, the synthetic seismogram can be, looks as close as to the observed seismogram. So normally people solve this question iteratively, means you adjust the model a bit, and then you generate the synthetic seismogram, and then you compare the synthetic with observed seismogram and to see if they are similar. If not similar, okay, then you're gonna further adjust model, okay? And then iteration 1 and iteration 3 and all the way to 12 iterations. As you can see that the fit between the black and red curves is getting better and better, okay? So basically, I summarize the idea here. So you just keep adjusting your seismic velocity model until the travel time difference or the shape of the waveform between the observed and synthetic seismogram is as small as possible. So that's a basic idea behind this seismic imaging method. Okay, so I think this is probably figure 2 from their paper, which shows the travel time obtained from like initial guess of the velocity model, the gray one. As you can see, 0 travel time means you have perfect fit between the synthetic and observed seismogram. So they are like identical, okay? So the gray one, you see there's quite a bit bias, right? It's a 10, so ideally it should be 0. So when you adjust your model, and when you get the final velocity model, and predict the travel time, which is shown in red, they are centered on 0. Okay, not perfect, but centered on 0. That means like you get a good match between your velocity model and the real structure. So that's the idea of this figure. And then the authors, they compared their velocity model, which is shown here, the first row. And the bottom 3 rows are the velocity model obtained from earlier works, all published in 2018. So they are quite recent velocity models. As you can see, that there are quite a bit difference between these models. But the good thing is the first order structures are kind of similar. So for example, you can see that they're like blue means fast, right? Fast is just a oceanic plate, and then you see this kind of red, which are the low velocity structures. So that's a good news. So the first order structures are similar. I think I'm gonna pause a bit and maybe ask a question. So which one do you prefer? Like all these 4 models, which one do you think is the best? Okay, then I will. Well, I will say, if you're talking about the method, I think the one investigated in this paper is probably the most advanced seismic imaging techniques among all these 4 works. And if you look at the details in the model, yes, this one shows like there's a lot of details, right? Compared to the second one, this one is like very smooth model. But sometimes more details do not necessarily mean higher resolution. Okay, or in other words, more details do not necessarily mean better. It really depends. I think the authors even acknowledge in the paper some of the small scale anomalies, like here and maybe somewhere here, and they are imaging artifact, means they are probably not real listed structures. So that actually come to like typical questions for seismologists. Don't try to interpret everything you see in the velocity model. Okay, just focus on the key structures, and these small scale anomalies may be just imaging artifacts. All right, so the authors are smart. Okay, they just focus on the kind of important structures. And in this case, they have like 4 high velocity structures labeled as H1 to H4, and then 6 low velocity structures labeled like L1, L2 to L4, 5, 6. Yeah, this 6 low velocity structures. I'll come back to these figures later. I will see you'll find these figures a couple of times. So this is a cross-sectional view of their velocity model. Essentially, they just cut across the velocity model along these 4 profiles. And AA prime for profile is going across the Aleutian Alaska subduction volcanic arc. And BB prime is going through the gap area. And CC prime is going through the WCJD volcanoes. And the last one is cutting across the Wrangell volcanic field. So these high velocity structures, they interpret it as the subducting oceanic plate. And on AA prime profile, and this is the Pacific plate. And if you're moving on to CC prime, and then H3 is represent the what they call Yakutata. Yeah, it's difficult to pronounce. Yakutata plate, and the last one H4 is stands for the Wrangell plate, I think. So, and then this low velocity anomalies, as you can see, they are kind of different from one profile to another. Like for example, in AA prime profile, you see this kind of very low velocity anomalies in the mantle wedge, and then at greater depths, you'll see this kind of slightly higher velocity, low velocity anomaly, and BB prime compared to AA prime. And here is essentially dominated by the high velocity structure. And then moving on to CC prime, you'll see this kind of a blob of high velocity structures close to the volcano. But here you have low velocity structures. And DD prime, again, you see low velocity structures beneath the volcano. And here is another weaker low velocity structures. And all these kind of structures are related to the kind of dynamics of the volcano, which I will explain further in the next few slides. So, typically seismologists just interpret the velocity structures based on the colors and also the strength or amplitude of the colors. But the author did like one step further. So they did some more quantitative interpretation. So what they did is they extract the velocities beneath all those kind of volcanoes and at 3 different depths, and 80, 51, and 28 kilometer depths. Okay, so the color corresponds to well, the red color corresponds to AA, so it's Aleutian arc, and the blue one corresponds to WVF and this cluster, and these 2 green circles correspond to these two isolated volcanoes, BCGD group. So I would not dive into much details here because I think most of the concept illustrated nicely in the last figure in the cartoon. But here I would like to point out maybe just one feature here. So at 28 kilometer depths, and you can see that the blue group, which is the WVF, it shows much lower velocity compared to all the other groups, right? And also the black dashed line here is the regional average. So that means here the velocity is anomalously low, okay, compared to the regional average. And this low velocity, they also attribute them to the large amount of magma at shallow depths, 28 kilometers, which is I think crustal depths. So it's a big magma body in the crust beneath the WVF volcanoes. Okay, so this one is quite similar to the previous figure. So instead of showing 3 independent depths, it shows the depth profile beneath all the volcanoes. Again, we can see the left figure is the absolute velocity, okay? The absolute velocity, and the right figure shows the velocity perturbation. Basically, it tells us like how the velocity profile compared to the regional average. So again, we see for the WVF group, and there is a very significant low velocity residing at around 30 kilometer depths. So which is much lower compared to all the other groups investigated in this study. So this, you may find this is very interesting figures and somehow a bit confusing. Well, at least when I first see this, when I was a graduate student, I find it quite confusing. And also very interesting. So which we call it resolution test or hypothesis test. So the idea is like, so sometimes you cannot believe whatever you see in a velocity model. So like here, right, this is a kind of important argument in their paper. They rather than like the one shown in previous study, so this slab is kind of continuous structure. What they see in their paper is this slab actually consists of 2 sub-slabs, so 2 parallel high velocity structure. So this may raise some concerns because some of them may say that is a resolution of your data or method high enough to distinguish this kind of slow velocity, this kind of small scale velocity structures? Or in other words, how can you convince us this is a real structure, not imaging artifacts? So in order to answer this question, the author did the so-called the hypothetical test. So the idea is you just use a design of a velocity structure which resembles what you see in the real structure. Okay, so this one just mimic these 2 parallel slabs. And then You use this model, you run your simulation, you get your synthetic data, and then you treat your synthetic data as if they are real observations, and then invert for the structures with the synthetic data. And then you get the so-called recovered model. So by comparing the input with the recovered model to compare how similar they are, you can get an idea of the resolvability of this structure. So as you can see, like if the gap is 25 kilometers, you can sort of see two independent high velocity centers, right? And high velocity, then you have a weaker anomaly, and then a strong one. So they're kind of separated. And when you further increase the gap to 50 kilometers, and these two velocity centers, high velocity centers, can be well reserved. And well, that tells us, okay, if this structure is present in the data, then it can be, if this velocity structure is a real structure, it can be resolved by the data and the seismic imaging method they used. Okay, so that's the idea of this test. And then the authors provided like two end-member slab models and to interpret their seismic observations. The first one, shown on the left, is basically attribute the slab to a continuous structure. So all these structures, high velocity anomalies, are kind of connected, but the low velocity structure in between and attributed to the weak zones. So essentially, they think this is kind of continuous structure. So on the other end of the spectrum, so we have this kind of independent slab model, right? So the Pacific slab and the Yakutat slab, they're like two separate slab, two independent slab, separated by the tear or gaps. And also this small Wrangell slab is also an independent one that is detached from the Yakutata slab. So that's basically two end-member slab models. And the author mentioned in the paper, in order to understand their formation mechanism, some other works, including geodynamics and modeling, is further required. So they didn't give a specific interpretations of why they have this kind of slab gap or slab tear. Okay, so this is the interpretation, and again, this is a cross section you have seen in the previous slide, and that is a cartoon, the interpretation corresponding to each one of the profile. Yeah, I'm a person. I always talk to my students. I'm the person who really appreciates this kind of a cartoon because it conveys the idea clearly and nicely. So let's look at each one of the profile. So on AA prime, right? So you have this high velocity and three low velocity structures. And the high velocity is simple, it's just a Pacific slab. And then you have L5 and L4, and they have different formation mechanism. So L5 is just a fluid. They interpret it as a fluid and dehydrated from the sediments. And L4, in this case, is the serpentinized mantle wedge. So because the serpentine has low seismic velocity, so that can effectively lower the velocity in the mantle wedge. And then the L1 anomaly here, they attribute it to the mantle upwelling. So you have a downgoing slab, and then it presumably just splash those kind of or perturb the mantle, and then it's caused this kind of upwelling on the other side of the subduction system. So then the magma of the Aleutian volcanic arcs is coming from the fluid dehydrated from the slab, and this one can facilitate the partial melting of the mantle wedge, and then it feed this kind of volcanic system. I'll skip B prime and come back to later, and then let's look at CC prime first. And CC prime is different from AA prime. As you can see, it has a quite strong high velocity anomaly. And also in the mantle wedge, it doesn't have like distinctive low velocity anomaly as seen on AA prime. So in this case, the BCGD volcanoes, the magma is mainly coming from the upwelling or edge flow from here. So it's not like A prime where the dominating mantle, the magma is coming from the subducting slab or the fluid from the slab dehydration. And for the DD prime, the Wrangell volcanic field, and the magma is actually coming from like two sources. One is similar to A prime, is due to the fluid dehydration, the dehydration from the downgoing slab. And another part is from the mantle upwelling. As you can see, there is a low velocity anomaly going all the way from the bottom of the velocity model and kind of connected to the volcanic field. Okay, so all these profiles, they show significant low velocity structures in the mantle, right? But for VV prime, the story here is quite different. So in the mantle, but by the way, the black dash line, I think it represents the mohole, it marks the mohole. So in the mantle, it's dominated by the high velocity structures, okay? So the authors interpret these high velocity structures as the delaminated mantle lithosphere, and it is cold and dry. So it prevents the system from generating the melt. In other words, there is a melt deficit in the mantle wedge. So it cannot provide any magma to the volcanic arc. So that explains why there is a gap in this area. So because of quite different mantle structures, and presumably also the mantle dynamic is different. It doesn't have the return flow, mantle upwelling, as we have seen on the other three profiles. So I think there's the last one. It should be a fancy movie from, I don't know if I can play this. Okay. A fancy movie from their paper. So they essentially get stuck. Okay. Yeah, they plotted this is isosurface plot. Okay. And this is a subducting slab, Pacific plate and Yakutada plate. And then those are the volcanoes, Aleutian volcanic arc. And this is two BCJD and the other one. So you can see those low velocity structures underlying those kind of volcanic fields, which feed those volcanoes. Yeah, as you can see from Xiaotao's paper, last figure is always the cartoon, the interpretation. Yeah, which I think is a very effective way to convey the science idea. All right, I think that's pretty much it. Okay, yeah, that's all. So I'm happy to answer any questions you may have, or we want to discuss anything about seismology.
Okay, thank you very much, Yunfeng, for leading the paper. So if you have any question, feel free to open your mic or type is okay. Okay. Actually, from my perspective, that if they are right, then if there are independent studies using the electromagnetic studies, then likely they should see this high conductive layer. Should be, like say, for example, for some of the volcanoes that are underlined by high velocity slab, and they are claiming that they have a low velocity mantle that beneath that. So that's why that some of the volcanoes could let's say could form, right? Yeah. But to me that basically this kind of like say multi-layer structure as what they claim. I just don't know. I could not judge that how reliable you would trust their models, because there are certain assumptions they put here, but I don't know their resolution either. But if there are certain high conductive layers coming from independent status, probably that could, let's say, basically nail down at least some of the low velocity parts as what they had mentioned about in this paper.
Yeah. I think electromagnetic is probably a better imaging techniques, geophysical imaging techniques to image this kind of volcanic system. Like there's a recent paper, I think Nature paper, and they imaged the Yellowstone area, and that one can really gives high resolution image of the volcanic system. It can actually target on one volcanoes, okay, to image the magma chamber and everything beneath it. But I'll say the sizing model, you just provide kind of like a background, okay, a first order structure of the entire area. So it may be, okay, my point is it's good to show like the slab, let's say here, right? You can actually image the slab very well, but it'd be tricky to interpret this kind of independent, isolated, low velocity structure. But because you see the size of this kind of anomaly, some of them are actually kind of close to the low velocity structure they showed. So but I think the general idea of this paper is kind of clear. So all these volcanoes, they are kind of related to the low velocity structure, and the low velocity structure either caused by the mantle upwelling or the serpentinite or the fluids from the dehydrated slab. So I think the connections are kind of clear, but yeah, the small scale anomalies, that is always a challenge, and to interpret this kind of small scale structure.
Yeah, Ben has a question. It's more about whether this applies globally.
It could be done, but it's gonna be difficult. Yeah, it could be done, but the thing about like the resolution of the seismic model, if you do a like I don't know, like maybe one can check some of the existing global seismic model to see if you can actually find any correlation between the low velocity structure and volcano. My guess is gonna be hard because the resolution of this model on the order of hundreds of kilometers. Okay, so you basically you really need to do some regional scale seismic imaging. So you can study, say, this is Alaska Aleutian, and then somebody may study Western Pacific, and somebody else may study South America, and to have this kind of case studies and then piece them together, then probably can partially answer your question to see if there's any correlation globally, but it's gonna be difficult to use a global model to do this.
Hello, could you hear me? I'm Xiaotao.
Yeah.
Nice talk, I think. So could you explain more about the last, I think in the last two slides, and explain more about why there's no volcanoes beneath the gap area? It's just about because in this paper, I think they also just using the elimination of low crust to expand it, and because I don't know details of that, and if there's no volcanoes, means that the volcanic activity in this area is very low. So if it's right, I think it has more implications because in the whole history of our Earth, there are some periods the volcanic activity is higher, and in some periods there's some violence of the volcanoes. The volcano activity is very low. So I think maybe it has some most important implications if this is right.
Yeah, yeah, that's a good point. So in this paper, they mainly attribute to melt deficit. So essentially, you need to have melt in the mantle, and then the melt can transfer upward and to form the volcano, right? So if you don't have melt in the mantle, then it's gonna be difficult or impossible to have a volcano. But they only briefly explain why there's no melt, okay? No melt in the mantle. And what they argued in their paper is you have this cold and dry delaminated mantle lithosphere. And this thing just prevents the dehydration and the migration up deep, okay? Up deep or upward migration of the fluid of the slab. So I think what they mean maybe just if you don't have the fluid, okay? Because the fluid gonna facilitate the generation of the melt in the mantle, right? And if you don't have fluid, then that probably is less likely to have this melt. And if you don't have melt, it cannot fit the volcano system. I think that's probably the logic behind their paper, but they didn't really talk much about why there's no melt.
But it is not convincing, the interpretation. I think for two reasons. You look at B here. I mean, this B below. So if they have a cold and dry delamination, then for the rest of the white parts that lying between the slab under the volcano or somewhere, so with all these white areas, so if according to other cartoons they draw, that should be fulfilled by the convective mantle, which should have a higher temperature. So yeah, so if you really delaminate, probably they will make the temperature in this white part higher. So it's preferred they don't delaminate, just staying there, probably is better. And another thing I think also, I think it's against what they are talking about is that as far as I could recall that when I was at Scripps, I saw a poster about Carrie Key's work publishing, Carrie Key group's work published in Nature, where they use the electromagnetic studies where they could show very nicely for the subductic slabs. You could see those fissures of those cracks that are filled with fluids, basically. And basically for the Yakuta slab or whatever slab, you see many fissures. And for each fissure, you see very high conductive. They're highly conductive within them. And those are the percolating fluid. So I don't see the reason why there's no fluid at this point. At least they didn't draw it perfectly, because the cold and dry only prevent some of the fluid going in that direction, but didn't prevent others, because there's still gap. Also the word delamination right there. Those words in a wider background happen to be the place, I think, perfectly for fluids to migrate there, from the east to west, or from right to left, or for a asthenosphere mantle with higher temperature migrating from left to right, or from west to east. So that's just what I see from this. Maybe I don't think this interpretation will deny their work as a good work, but from my perspective, I didn't really get it, or I don't look at it as really convincing.
Okay, yeah. I think water play a role. Yeah, I agree with you. I think most likely there are gonna be fluid released by the slab, but I don't know if the temperature can play a role as well, because compared to the all these 4 profiles, right? This one is most likely to have lower temperature compared to all the other 3. Due
Yes,
to the presence of cold and dry slab. Yeah, that may change the mantle dynamics in the mantle wedge as well.
Yes, I have another question. Is that paper just provide the age of the volcano, just the eruption age of the volcanoes? Because maybe the gap just that the volcanoes just do not erupt at the present, but maybe erupt in the future, I think.
Could be, means it's not active volcano. You mean not active currently?
Yeah.
Yeah, it could be, but I don't know. Like, is there any like rock samples and can support its status in the past, like what active volcano a long time ago, or then it's kind of become inactive.
Yeah. Thanks so much.
Yeah. But yeah, it's a good point, interesting point. And on Wednesday, you can throw these questions at Xiaotao. More question?
Yeah, Zhang Quan has a question.
Do the authors mention how to set initial input velocity anomalies, like the precise 10% in figure 8? Figure 8, which is figure 8. I forgot about the order of the figure. Initial, yes. I think they mentioned they for the I think for depths about maybe 100 or 200 kilometers or something, they use a recent velocity model from other people's work. And oh yeah, this one. Oh, okay. So about talking about hypothesis test. Yeah, this okay. This is I don't think there is a kind of a consistent way to do this. Okay, I did this as well in my paper, and it's essentially you have to parameterize your model space into grid, right? And then in order to design the structure, you really need to know how to assign the values to each grid. Okay, for this one, I think it's not that difficult, because think about it, this is a rectangle, right? Rectangular shape, but it's not like kind of regular shape. But you can define a center of this rectangle, and then you can define the length and also the orientation of the structure. Okay, and then well, there's gonna be some details like how you implement the code, but basically, as long as you can define the center of the structure, and also it's the scale, like ladder scale and vertical scale, and it's not difficult to do it. It's just a matter how you implement it in computer code. And for the anomaly, the size of anomaly, well, essentially you'll find something similar to your observation, but needs to be a little bit stronger than you observed, because the inversion gonna reduce the amplitude a bit. If you compare the input and recovered, you'll see the amplitude recovery is probably on the order of 40 or 60%. So you have to make sure your input, the amplitude of input anomaly is a bit stronger than your observation. Yeah, that's kind of a trick. So yeah. Okay.
Okay, do we have more questions from our participants today?
Well, I ask question. Why this? Why this paper or his work is kind of interest to the geochemist?
Oh, well, I think, like I say, for geochemists in general, that we're also interested in the Earth structure in the interior. I think just like the question that Xiaotao asked earlier on, I think it's a quite interesting question that we should rethink about it, because to me that it looks like the slope of the slab, if they are correct according to what they claim, that might be an important parameter that we should consider in terms of the frequency of the global volcanoes. Let's say within how many recent years of active plate tectonics. So even by that, I think it's quite an interesting observation that they made, and this mechanism could potentially be, let's say, could provide insights for us to propose or confirm through the geological volcanic data, because there are a lot of volcanoes that you don't see them now, but there are samples there showing that there were volcanic activity before, and since seismologists are not able to image those very old stuff, or you have no way of knowing that those old stuff they're all being destroyed by mantle convection, for example, then that could likely be something that we could consider the formation or frequency of volcanoes. So yeah.
Okay, that's a good point. So essentially, look at if any structural control on the volcano.
Yeah, it looks like that there are observations for what is going on today or the recent 10 million years could help people to propose more mechanisms that likely work in the past.
Yeah. Yeah, that's true. Actually, to go back to Ben's question, yeah, I think it's going to be interesting to look at this more systematically, to see if this kind of ideas in this paper can explain all the volcanic systems in the world. Well, I doubt it, but this is just one potential mechanism. But yeah, it requires a bit more thinking in order to fully understand, the volcanic system around the globe, I think.
Yeah, and another thing that I think this work, let's continue with my previous statement, is that, okay, if you look at the temperature of the Earth from beginning of the Earth until today, it's always cooling, because even nowadays we have secular cooling, losing a small amount of heat to space every year. So if temperature is the only controlling factor, then the Earth's number of Earth's volcanoes will shrink with time. It's not. Actually, I don't know how it looks like. Maybe Xiaotao could tell us. But obviously, there are at certain times that volcanic activities are more active in the geological history that we could track than some other parts that looks like more silent. So obviously, temperature is not the most important controlling factor for global volcanic activity. And maybe for, like I say, for a very short time in the US, for example, there happen to be some super plume. That could be, but if you really look a long time, that probably the temperature is generally going down in the Earth's surface and also in the Earth's mantle too, but not for the volcanic activity. So some other factors must play a role here.
Yeah. It's probably controlled by the deep Earth process, because in this study, I think most of the volcanoes are attributed to shallow process, like subduction system.
Well, I think that leaves a lot of room for geodynamists to work on, because yeah, I think geochemists could help to provide some observation, but I think detailed mechanisms are geodynamists' job, telling us what are the reason to explain the volcanic activity pattern and why our volcanic activity in the Earth does not shrink with time as the temperature drops.
Yeah.
Okay, I think that's all, I suppose, of today. And thank you again for leading the discussion, and thanks everyone for your participation. So on Wednesday, we're going to see the speaker. So he's going to give the talk, and yeah, you could ask a question we talk about today, or think some new questions that could challenge him. Okay, have a good evening, everyone. Bye-bye.